This is where we left off from last time. Today is the 7th, 8th, 7th, and subspaces. So when we're dealing with matrices, it turns out that there's some built-in subspaces that come with matrices, and two of them are discussed in the book. There apparently is two more. Uh, that we might, one of them we'll see later on, the other one I'll introduce sooner, and that's the row space. Because I think it's easy enough to discuss, oops. It's easy enough to talk about row space and column spaces in the same venue, so let's throw in another definition here. The row space of a matrix A is the set row A of all linear, it's just like the column space, combinations of the rows of A. And so the ideal thing to do is to take a matrix and then plop it down and study its row space, column space, and null space. And then maybe we'll find some information about them. Maybe we'll find relationships between the different aspects of the particular matrix. And I think they only stuck with the column space and the null spaces because they define a lot of the stuff. They define the matrix as a collection of vectors that's written in columns. So that's really probably why they focused on the column space. And then the null space is just something that needs to be discussed anyways. So the row space seems to be something that, according to the textbook, didn't really matter so much. But it's easy enough to discuss and to talk about, so we will discuss and talk about it. So I was gonna sneak in to the book and take an example. And is that big enough? There's a guy in my other class who always says, "Can you make it larger?" He needs glasses. Okay, so a column space is the space that's spanned by the columns, and then the null space is whatever the null space is. Let's take a look at the column space, and before we actually try to find the column space, let's find out the vector space that it lives in. Because remember that these are subspaces of some other vector spaces, and the vector spaces that we deal with are the ones that we're going to focus on are R2, R3, R4, R5, etc. And so the column space needs to be a subspace of one of those spaces. Now the question is, what is it a subspace of? You understand my question, my approach? Okay, so that's what we probably should figure out first, and then we'll do the necessary math to figure out what those spaces are. So if we take a look at a column, how many elements does a column have? 3. So where is the column space? So column space should be a subset or subspace of R3. So these are 3 vectors. We'll call them vector A1, A2, A3, A4. So 3 minus 9, positive 9, for example, is A1. and it lives in R3. So your column space has to be in R3. Now, last time we talked about all the possible subspaces of R3, right? So what are our possible subspaces for this column of A? It's either just the origin, a line, and or a plane. Now the line or the plane has to pass through the origin, remember, right? Or the last option is everything, right? So those are the 0-dimensional, 1-dimensional, 2-dimensional, and the whole thing 3-dimensional possibilities for your subspaces. Now, I said 1, 2, 0, 1, 2, 3, 3-dimensional, right? I have 4 vectors here. What can you immediately say about these 4 column vectors? One of them, at least one. So there could be 2 of them that are linear, or it could be all 3 of them that are linearly dependent from each other. But if there's 4 vectors in a 3-dimensional space, we know that all 4 vectors will be linearly dependent, because that's too many, right? Is that making sense so far? So I'm going to try to remind you of all this vocabulary and see if we can make sense out of it. So this is the stuff that we've talked about already, and it's always a good reminder to try to figure out where you're living in temporarily here, and then what kind of scenarios we have. Just as a yeah, so right now all we know is the collection of 4 vectors are dependent. Right. So we don't know if one is dependent on the other 3 or 2 of them are dependent on the other 2 or what. But right now, all we know for sure is that it's dependent. We don't know. Yeah. So it seems like we want to be able to say something like that, right? But we're so do you understand our question? That's an important aspect to look at. There's 4 vectors. We're in R3. Are we guaranteed that this is going to be a 3-dimensional space? The answer is no, because we don't know how many of them are independent. There could maybe they're all linear, maybe they're all scalar multiples of each other, and this is only a 1-dimensional space. Or maybe 2 of them are, maybe all 3 of them, and then in which case that's the scenario. If it could be 3 of them are linear independent. But if you have 4 vectors, it's impossible for 4 vectors to be linearly independent in R3. Okay? Well, the idea of inconsistent is a little bit different from here, because we don't know if it's an augmented matrix or if it's whatever. So inconsistent is a little bit of a different topic. Okay? All right. So how do you think we can approach this? How should we try to figure out yeah, the Row-Echelon form will help us, right? Like when in doubt, just reduce it and see what happens. All right, so we're focused on the column space right now. Let's reduce it. I'd really just like to, yeah, thank you. Where's my program? I'm going to use MATLAB in case there's any kinks in Octave. Oh, there are some problems here that were already row reduced, and so maybe I should have gotten those instead. Or am I? I need my command window. Here it goes. So A equals 3, 2, 1 minus 5 minus 9 minus 4 minus 4, 1, 7, and 9, 2 minus 5, 1. Oh, I just hope we don't have any decimals. We're probably going to have decimals here. No, look at that. So we row reduce and we get this. So in our reduced row echelon form, we get this. So let's take a look at it. We have pivot column. And then we have 2 pivot columns. Yeah, 2 pivot columns. So we would have free variables here for looking at the free variable aspect of things. So this is what we have. What can you say about the? This is just A. This is not an augmented. X3 and 4, if we look at it, yeah, would be free. We're going to look at that as another aspect of this when we take a look at the null space. So right now, in terms of the column space, we have 2 columns here that are pivot columns, and then the others are not pivot columns. And so that pivot column over here will correspond to these 2 vectors that we have. So it's going to turn out that these 2 vectors from the original matrix, A1 we called it, 3 minus 9, 9, and A2, 2 minus 4, 2, are linearly independent. And then the other 2 vectors are dependent on those 2. And another way to say that they're dependent on the first 2 vectors is that they are in the span. I guess we say span braces A1, A2. Which means you could take 1, 1, negative 5 and write that as a linear combination of A1 and A2. And you could take minus 5, 7, 1 and write that as a linear combination of A1 and A2. So it turns out that this is a 2-dimensional, because there's 2 linearly independent vectors, this is a 2-dimensional subspace of R3. Okay. So call A is equal to the span of A1 and A2 is a plane, a 2D subspace of R3. Jessica? Because it's a subspace, and subspaces always have 0. The 0 vector has to be in there. That's by definition what a subspace is. But some people might be curious to say, how do you know that this actually is a subspace? And the thing is that these are spanned by these 2 vectors. The column space is spanned by the column vectors. And so whenever it's spanned by something, you're not offsetting yourself to not the origin. You're always at the origin from the beginning. Because these vectors are always spanning from the origin. Yeah, you could. We always think about it as starting from the origin. Probably need a better answer, but that's the best I can come up with right now. Chris. Yes, maybe. Maybe you can hold on to that question, and when we start doing row spaces, see if it does make sense to what it is you're talking about. I don't know if I fully got your question. Anything else? Okay, so we're also jumping over here. You know, I'm talking about dimension. This whole idea about dimension is dependent on some other facts that's covered in the next section. So we'll take a quick look at that. But right now, we're looking at the two linearly independent vectors. The number of linearly independent vectors that span that actually will describe the dimension of the subspace that you're talking about. Had we found three linearly independent vectors, then we would be looking at a three-dimensional space. Okay? Just a vector space. Well, in this case, it would be the whole vector space R3, because that's where we're at. Well, technically, the whole space is considered a subspace also, right? Like zero, just the zero vector is considered a subspace, although it's just that itself. And then the whole thing is considered a subspace. Yeah. Then it would just be a line passing through the origin. And that line is exactly going in the same direction as that vector that you found. Yeah. Yes. I suppose, yeah, the number of pivot columns, if once you row reduce, would determine the dimension of the subspace. In this case, we found two pivot columns, so we took a look at the two vectors that span it, and that's a two-dimensional space. Yeah. Well, it couldn't be because you need at least one pivot column, right? Oh, I wish we could just create a hologram where you can just look at these things, especially in 4 dimensions. I guess we're still in 3 dimensions here. So if we take a look at these two vectors and we plot these two vectors, that's a span, then that would create your plane in 3 dimensions. And then everything else would be within that span of the plane. Okay? Yeah, one more.
How would we, because we're looking at the columns, how would we do that? Would A3 be like?
Should be. So A3 is 1, 1, negative 5. And this should equal to something times A2 plus something else times A3. And we should get values for that. Now we can guess and check. Maybe I'll take a stab and put 1 and 1. No, it's not going to work. I don't know. We'd have to do a. Let's see how we can get 5. Yeah, so you could actually get values for this. We could set up another matrix to find this, but we can set up the values for this. Okay, so let's go to the null space. Let's take the same example, and we might as well take the. Let's take a look at the null space. Remember that the null space is all the x vectors that would give you 0, right? So all the possible solutions. Now, let's figure out where the null space is. Where does the null space live? So I'll narrow it down for you. It's either an R3 or an R4. It's R4? Sure, it's an R4. Okay. So if we pretend that we're solving for this system, we can put the zeros there or not put the zeros there. But the idea is that we have a times x is equal to 0. Now, to make this matrix multiplication work, your x has to have the same number of elements as the number of columns that you have, right? So this would be x1, x2, x3, and x4. So your null space, I guess they use one less L here. Null A is in R4. Four-dimensional space. Now, unfortunately, we're not going to be able to see that anymore, but we can still imagine in 4D, if you close your eyes and think really hard and maybe get a hit. Then you can possibly visualize the idea that in four-dimensional space, you can imagine a point, a line, a plane, or a three-dimensional space that's one dimension lower than your four-dimensional space that you live in, or the whole thing. But the idea is that null A, in this particular example, is a four-dimensional subspace. It's a subspace of R4. Okay? And all we really care about is what's going to span that. So let's see, what is going to span that? We have the row-reduced version of the matrix, right? We found the pivot columns here, which means these are free variables. Now we can talk about free variables because we're looking at this system where you have an x in there. So these are the free variables. So we got x4 and x3 are free variables. And then you'll have, what will you have? You'll have x2 is equal to, and bring this over to the other side, minus 2x3 plus x4. And then x1, bring that to the other side, will be positive 1x3 minus 1x4. I don't know. Yeah. Whoops. Negative 4x4. Positive 4x4. Okay, so what do we have? We have your solution for this equation, for the homogeneous system equation here, is going to be x is equal to x3 minus x4 minus 2x3 plus x4, x4, x3, and x4. And then you can split this up, right, into two vectors. A vector that's being multiplied by the scalar x3, and then you would have a 1, minus 2, 1, and 0. And then you have another vector being multiplied by x4, and that's a negative 1. That's the coefficients that I'm looking at. Positive 4, 0, and 1. So these two vectors span the null space. Yeah. So the null space, where the null space lives, depends on the number of columns you have, because that's the number of variables you have in your system. So in this case, we have 4 columns, so our variables will have 4 variables. And so your null space has to have 4 variables, which means it has to live in R4. What? That didn't help. I mean, if the dimension of the matrix was, instead of a 3 by 4, if we had a 4 by 2 or 3 by 2, then your null space would live in a smaller space than your column space. So it depends on the dimensions of the matrix. Yeah.
In this case, x1 and x2, how we have it represented here, are linearly dependent on x3 and x4. Good. So x1 and x2 can be represented as linear combinations of x3, like x2 can be represented as a linear combination of x3 and x4.
No, we don't want to say that, because the x's are, in this particular scenario, the x's are not vectors. So we can't say a non-vector is linearly independent to other non-vectors. And so the variables x3 and x4 are dependent on, but they're not vectors. So we don't look at it that way. Okay. Good question. Anything else? Yeah. These two independent vectors, they span a two-dimensional space, but it's not R2. They span a two-dimensional space in R4. Because, so null A lives in R4, it's not all of R4. So the null space is a subspace of R4, but it's not all of R4. And in fact, in this case, we found that the null space has two linearly independent vectors. And so the null space is a two-dimensional plane that lives in R4. And all of that is null space. Everything on that plane is null space.
Linear combination of the two vectors is equivalent to null A.
The linear combination, the span of it, yeah. Which means if you give me any two numbers and then I put it in for x3 and x4, I'm going to get a vector, right? And if I multiply that vector with A, I'm going to get 0. You understand that part? So give me a value for x3 and x4. x3 equals 1, x4 equals 2. So x equals 1, and then this is times 2. So 1 minus 2 is -1. -2 plus 8 is 6. This is 1, and this is 2. Okay? So this vector is a vector in the span of those two vectors, right? So what does that mean to be in the null space? So that vector is in the null space, which means if I multiply A times that vector, so I'm going to write this vector in MATLAB as a row vector and then take the transpose of it. So it's a row vector, and that symbol apostrophe is transpose. So now I can multiply this. I should get zeros. 0, 0, 0, because it's a linear combination of those two things. And I was thinking the other way. So the linear combination of those two vectors is everything in the span that these two vectors can reach. Right. So these two vectors reach everything in the null space, which in this case is a plane in a 4-dimensional space. Yeah. Well, no, the matrix is not in a particular R space. So, I mean, if we want to be technical, the matrix is in R12. But that's because that's how many numbers there are. So the columns are in R3, and the null space is in R4 because there are 4 columns. Okay, and the null space is a 2-dimensional vector or 2-dimensional subspace in R4. Okay. Yeah.
Those two vectors independently span
Mm-hmm.
in R3.
Yes. So
the subspace of R3.
That's the column space.
That's the column space. So the null space is essentially the other two vectors which don't include, which the null space is another plane that lives in R4 space.
Right.
And that doesn't include the original.
It wouldn't have too much to do with the other. Yeah. Because they're in 2 different spaces. 2 different vector spaces. Well, it turns out that there's a relationship between the dimensions of the column space and the dimension of the null space. And so we're in 2-dimensional vector space. We're in a 2-dimensional subspace in the column space, and our null space is a 2-dimensional subspace. And so if you add those 2 dimensions, you get R4. That is a theorem. Rank. It's called the Rank Theorem. It's just rank. So usually linear algebra textbooks focus on the row space before the column space, because the row space would be, what was the row space again? The row space of the matrix is a linear combination of all the rows. So if we take a look at the rows instead of the columns, then the rows are 4-dimensional vectors. And so we could take a look at the span of these 3 rows and imagine where they live. So let's take a look at the row space now. So if we take a look at the rows, and each row is a vector, what dimension are we looking at? So each row is a vector in R4, right? So the row space is a subspace of R4. And it's going to be spanned by these three vectors. So the question is, are those vectors linearly independent or not? So after we do the row reducing, we see that we got a row full of zeros, and then we have these two rows. So these vectors are, or make up the span. They make up the span of the row space. Yeah. I don't think it matters, but the idea of a transpose says the column space and the row space can be obtained kind of like the same way. In fact, that's the fourth kind of subspace between here, is something to do with the transpose. Wait, these vectors make up the span of row A. These vectors? So 1, 0, minus 1, 1, 0, 1, 2, negative 4. So this would be a two-dimensional plane in a four-dimensional space. But wait a minute. When we did the column space, we went back to the original matrix. So if I take a look at the rows here, 3, 2, 1, minus 5, minus 9, minus 4, 1, 7. Shouldn't these span the row space? So which one should span the row space? Okay. So it turns out that these two span the same space. One quick way to check, I don't know if this will be quick, but one quick way to check is that we can try to find a linear combination, a vector that's in the span of this, and show that it actually is also in the span of this. So if we can find a vector here by finding a linear combination of random two numbers again, and then show that it's also in this, then we can say that they essentially would be spanning the same space. And more importantly, it's because they're row equivalent. So the way we got from the original matrix A to the reduced matrix is through basic row operations. So imagine what you're doing in your row operations. You're multiplying it by a scalar and adding it to the other vector. Multiplying it by a scalar and adding it to another vector. All you're doing is taking scalar multiples of things and then adding it, so that's just linear combinations of things. And so you're not changing your space by doing that. We've eliminated one of those vectors to say that this last vector here is really a linear combination of the other two vectors. That makes it dependent. And so we're left with only two linearly independent vectors. Okay? So the row space is in R4. The column space is in R3, but the null space is also in R4. So the row space and the null space are both in R4, and one's two-dimensional, and then the other one's two-dimensional. I wonder if these two planes intersect. I wonder if the null space and the row space will have any vectors in common. What do you guys think? Okay, aside from the origin, do you think those two subspaces will have anything in common? So they should have a one-dimensional thing in common, right? No. Only the origin. So these two vectors will be, anyways. Perpendicular. These two spaces are perpendicular to each other. It's in 40. Yeah. Wow, that blows everything. So let's take a look at something in 2 dimensions. So in 2 dimensions, we can imagine a null space to be a one-dimensional vector, or a row space to be a one-dimensional vector. So it turns out that they will intersect each other at the origin. Then now the interesting thing is that they will intersect each other perpendicularly. Okay, let's go to R3, the possible subspaces, right? Possible subspaces in 3-dimensional space is either a point, a line, a plane, or a space, the whole thing. Now, if your null space is one-dimensional and then your row space is two-dimensional, then they would intersect at the origin. Okay, not only that, but they would also intersect perpendicularly. So these things will end up being perpendicular to each other. And that's something that we'll see in chapter 6. Ooh, heavy stuff. Yeah. If you take these, so A times 1, 0, minus 1, 1, and I need to prime it. No.
No, I mean the expression x4 and then the vector -1, 4, 0, 1.
Oh, it's from the previous page, from the null space? Yeah, because they're in the null space. But everything here is in the vector space now, so in the row space, which is not in the null space, which means any of these or any linear combination of these vectors in the row space should not, never give you 0. So if I change this into the other one, or even change it to the first row, like if I change this to 3, 2, 1, minus 5, I shouldn't get 0 because it's not in the null space. I think you were looking at the previous.
Yeah.
Yeah, and this is all about the null space. So everything in here would give you 0. Oh, yeah, yeah. Okay. Is this heavy? Got about a third or a quarter of the class that's really paying attention into it. Others are just kind of looking at the computer and writing stuff out. Well, the row and column space live in the same space, but they're actually mutually exclusive except for the origin. They don't share anything at all except for the 0 vector. No, I'm sorry, the row and the null space. And they're perpendicular, and they only share the origin. Yeah. No. The row lives in one. In this case, the row was in R4 and the column was on R3. So they're both two-dimensional, but they don't share the same space. They're not the same space. All right, the null space. So let's throw some more definitions here, and we're talking about basis vectors. And these are some facts that we kind of already have discussed and already kind of know. So there's a theorem that says the null space of an M by N matrix is a subspace of Rn. That's the number of columns you have. Equivalently, the set of all solutions to the system AX equals 0 of M homogeneous linear systems in N unknowns is a subspace of Rn. But that's pretty much what the null space is. So, kind of don't know why they said that. So when we're dealing with spaces and subspaces and vector spaces, we want to know this thing called a basis. A basis for a subspace is a set of all linearly independent vectors that span the space that you're talking about. Now, in the case of Rn, R2, you have the ij vectors. R3, you have the ijk vectors. Those are your standard basis vectors. And what we found in the previous pages were basis vectors for the column space, the null space, and the row space. Okay, so this is getting towards the column space. The pivot columns of matrix A form a basis for the column space of A. So this is the first example that we did, where we took a look at the pivot columns, and then we took the columns from the original matrix. And then there's one more piece of information here. Is there one more piece of information? Nope. It's a warning. All right, let's see if we can do another one. These are all larger. I want it to go R3. All right, if we can't go small, let's go big. And in these examples, they gave us the reduced row echelon form already, which makes it nice and easy for us to, well, I mean, we could also put it into the computer. Yeah. That means many steps to row reduce. Equivalent, yeah, it means equivalent. That's the word. Let's even call it row equivalent. Okay. So once you've reduced your matrix, pulling out the basis vectors for the column space, the null space, and the row space become really, really easy. Okay. Yeah. Doesn't look like what? Yeah. Oh yeah, they didn't put the. I thought it was reduced, so it's not quite reduced row echelon, but let's work with this. First, the column space. Let's identify the pivot columns. So these are the pivot columns, and then I can identify them in the original matrix. That's the first column, the second column, and the third column. No, the fourth column. Okay. So this is kind of like the bottom line. So if you didn't understand any of the theory stuff, then this is really the way to do it. I mean, if you understand it, great. If you don't, then try to I don't know. Good luck. So column A, the subspace column A, is going to be the span of the vectors. Ooh, what? I need to make this bigger so that 3 minus 2 minus 5 minus 2, 1, 2, 9, 6, 3, 7, 3, 3. Negative what? Oh, negative 1. Thank you. You need to look back at the original form for it, yeah. Nope, nope. That's the tricky part about the column space. Yeah. So the row space, what spans the same space? Oh, that's for the rows. The columns are different. So you can't. So that's an important thing to remember is that you can't use the reduced form for your column. You can't use that. So be careful with that. Because you're doing it's row equivalent, but it's not column equivalent. So there's stranger things that happens when when you do row reducing. That's not your regular scalar multiple and addition business. So it's you can't use the original one. Yeah, or you can take the transpose and do row reduction, and you get the same thing. So the row space will be this one. You can actually take the rows from the reduced row echelon form. So in this case, it would be 3 minus 1, 7, 0, 6. Zero, 2, 4, 0, 3, and 0, 0, 0, 1, 1. So that's the row space. I did because I was running out of space. So now the null space. This is going to require a little bit of work. It's because you have to identify your free variables and then write your expression. So where are my free variables? My free variables, I have 1, 2, 3, 4, 5. So I would have 5 variables. The last variable I'll call x sub 5 is free, and the third variable is free. So I have 2 free variables, x3 and x5. And then I would want to solve for the others. So x4, if I look at this this row over here, x4 is going to equal to negative x5. Right? You bring the 1 over to the other side with the x5. The next one is x2, because x3 is free. x2 is here. Let me put, let's put 2x2 here first. And then bring the 4 over. The 4 is x3 minus 4x3, and then minus 3x5. And if I would have had an x4 in here, I need to do the replacing because I only want x3s and x5s in my solution. And then I can divide out the 2. So x2 is equal to negative 2 x3 minus 3 halves x5. Let me box these so I don't lose them. And then now let's go x1. So that's 3x1 is equal to, we bring the x2 over, we bring the 7x3 over, and then we bring the 6x5 over. Okay, now I have an x2, which means I have to put the x2 in. Watch. 3 halves x5 minus 7x3 minus 6x5. All right, so we got a little bit of fraction work over here. Minus 2 minus 7 is minus 9 x3. And then minus 3 minus 6 is what? 15 halves x5. There we go. Oh, I need to divide by 3. So x1 is equal to minus 3x3 minus 5 2x5. Now I can box it. All right, so what's our solutions? X is going to equal to, let's do this carefully, minus 3x3 minus 5 halves x5 for x1. x2 is minus 2x3 minus 3 halves x5. x3 is free. x4 is negative x5. And x5 is just x5. So now you split them up. So with an x3 is a negative 3, negative 2, 1, 0, 0. And then x5 will have negative 5 over 2, negative 3 over 2, 0, negative 1, 1. So the halves here, you can multiply this whole thing by 2 because since x5 is free, you can let it anything you want. So you can imagine scaling it if you want nicer numbers without having to deal with fractions. In any case, these two vectors will span your null space. So your null A is equal to the span of -3, -2, 1, 0, 0. And if you wish, multiply everything by 2. Oops, -5, -3, 0, -2, +2. So anything in this span will be in the null space, which is to say that if I take any number, any linear combination of these two vectors, and I apply it to the original matrix A, it's going to go to 0. Yes? Yes, this is a plane in R5. It's a three-dimensional space in R5. Well, what's column? So column A is going to be a three-dimensional space in R4. So the key thing here is that according to the rank theorem, which is in the next section, the span, the number of dimensions in row or column. By the way, the column space and the row space will always have the same dimension, even though they live in different spaces. Yeah, they will have the same dimension. But the dimension in the row space plus the dimension in the null space is going to equal to the number of columns. The dimension of the row space and the dimension of the null space will equal to the number of columns. And in this case, there are 5 columns in the matrix. Ooh. So this is as you could probably tell, it's a very theoretical topic. Actually, this whole class is pretty theoretical. And so it would be good practice to probably take a look at the theory. And so in terms of like multiple choice type questions, maybe I'm going to create some practice quizzes that will be worth no points, but you could take over and over again if you want. And then I'll post it in my math lab so that you can visualize or try to imagine the theory behind these things. And then I'll probably draw from those some, true, false, or short answer questions on the test. Okay, I don't want to make it homework because I still, you're going to have enough homework to do. So this will just be for you to go on your own. All right. Good luck.